the waiting room, so I'll make a start. Hello, my name is Sarah Bolton. I'm an Associate Professor of Active and Neotectonics at the University of Plymouth. And one of the things that I'm interested in my research and in my teaching are tsunamis. So I'm a geologist, and lots of different scientists are interested in the science of tsunamis, but geologists have a really important role to play in their understanding. So this afternoon, I'm going to take you on a bit of a whistle-stop tour from Japan to the United Kingdom, looking at 3 different events and the tsunamis that they generated. But first of all, before we start talking too much about tsunamis, I just want to say a few words about geology and earth sciences. So some of you might be familiar with what geology earth sciences is. It's the study of our planet Earth, and more specifically, it's the study of the history and the solid Earth rather than atmospherics or ocean or climate. And so as a geologist, we could study the origin, the composition, the structure, the history, the evolution of life and paleontology, but we can also study landscapes and landscape change. We can look for resources, and we study geohazards from a geological point of view. And that's important because geologists, we're time travelers. So that means we can go back in time by using the materials that have been formed through Earth's history. So much like archaeologists or astronomers and astrophysicists, we can go back in time and look at past events. But of course, there's problems with that, because as we go further into the past, things get blurry, a bit like this photo of train tracks. So things that have happened more recently, we've got lots of evidence for, and they're really clear. But as we go back in time, we have to piece together the bits of information, a bit like a detective, where we take the bits of evidence that are left and we put them together. So that's really important. There's an adage in geology that is the present is the key to the past, but also the past can be the key to the future. And so understanding what has happened in the past can help us think about and inform our knowledge of future events. And that's really important when we think about geohazards. The other thing that's really cool about geology is that it is an interpretive science. So planet Earth has run the experiments already, and the results of those experiments are recorded in the geological strata that we can go out into the field and have a look at. And so we can go and make observations on a range of different scales and put together those bits of information. But of course, that means bits are missing. And so we have to make interpretations based upon our knowledge and our understanding of what that might mean. But it makes it really interesting because we can do that sort of treasure hunting, geological treasure hunting. As a result of that, geology uses lots of different disciplines. It uses maths, it uses physics, it uses chemistry and biology to understand the way the Earth works. And as a result, there's lots of different branches of Earth science, from paleontology, igneous, geochemistry, mineralogy, and of course, people who are interested in geohazards such as tsunamis. And I just want to flag this up because a lot of people think that geology and geoscience is perhaps a bit dusty. It's looking at the past, or perhaps it's bad for the planet because geologists, some geologists look for things like petroleum. But I just want to really highlight that actually earth scientists, geologists of various different types have real key roles to play in mitigating the effects of climate change and making our planet a better place for everyone to live through working towards something called the UN Sustainable Development Goals. And they are a series of promises set forward by the UN to try and make the world a better place. And quite a lot of these are to do with geohazards and making our built environment and making landscapes more safe for people. And geologists can do this in a variety of ways. And so one way, what I'm going to be talking about more now, is about tsunamis. So let's go to Japan first. And many of you will be really familiar with this beautiful Japanese woodcut print made by Katsushika Hokusai in the 19th century. And this great wave of Kanagawa is often cited as being a tsunami, but that's probably not the case. This is probably more likely to be a typhoon driven wave, because this is not the typical form of a tsunami. Now, Japan is really interesting. It's got really long historical records, and there's also been a huge amount of work done on the geology and understanding of tsunamis in Japan. But let's just show why tsunamis are so important. These are really devastating natural hazards. They're often described as the tide does not stop coming in. So you can see in this video from the Tohoku 2011 tsunami that was the result of a large earthquake, that the sea just keeps on coming and it overwhelms everything in its path. And you can see the ships and the houses and the fire in the oncoming tsunami, and it's just overwhelming the landscape in Japan. And of course, anything in its way is going to be completely overwhelmed by that. And I will stop it here. It is a longer one. You can find it on YouTube, but it is really sad because we have to remember that people died in this event. But as scientists, our role is to try and prevent the catastrophes that happen as a result of the natural hazards. We can't stop the hazards themselves happening, but through understanding their frequency and their effects, we can help make communities more resilient and be able to respond when such events happen. So let's take a step back though. What's the difference between a tsunami wave and a normal wind-driven wave that we will see at the beach? Well, they're fundamentally different. So wind-driven waves are termed deep water waves. That means that there is no wave action below a certain level in the water column, and that water level is called the wave base. And there are two wave bases. There's the fair weather wave base and the storm wave base. So on an average day, waves will only create water motion above the fair weather wave base. A big storm will move the water to a lower depth in the water column, and that's the storm wave base. Below those, there is no or negligible water movement as a result of a wind-driven wave. And that typically is half the wavelength of the surface wave that you see. And you can see that these little circles represent water particle motion, in the water column. And so we've got the wavelength, the distance between the wave peaks, and we've got the wave height, the elevation difference between the trough and the crest. Wind-driven waves will break when they reach shallow water. This is very different from a tsunami wave. Tsunami waves are described as shallow water waves. I always find this a bit weird because you think of tsunamis being generated in deep water, but in fact it's the way they're defined. Tsunami is shallow water, and you can see here that the depth wavelength relationship is quite different from that of the deep water wind-driven waves. And a tsunami wave will move the entire water column. And you'll see that in this case, the water particles are going around in that direction rather in that direction. The result here is that the sea bottom, will feel the power of the wave motion, and so you get much more disruption of the sea floor. The other thing that happens is that you don't get this breaking when you get into shallow water, but conservation of momentum means that something must happen, and so the wave height increases as a result. So some key tsunami terminology: we have obviously amplitude and wavelength, just like we have with all types of waves, and then we can talk about things that run up, and that's the elevation above mean sea level that the tsunami wave eventually gets to. And we can also talk about inundation, and so that's the horizontal flooding distance from the normal shoreline inland. And so as geologists, we can go back into the rock records and try and find information about run-up and inundation. We can't really say so much things about maximum water level because that might be different from the eventual run-up distance. So how do we form tsunamis? Well, there are a variety of ways we can generate tsunamis. Earthquakes are one of the main ones that I'm going to be talking about today, and these have been in the news a lot recently and in the recent past. There are also landslides, and I'm going to talk about a landslide called Storega, but we can also generate tsunamis through volcanic eruptions, through bolide or meteorite or comet impacts, and of course there can be combined sources, and these are often called cascading hazards. And that's what Tohoku is, but we could have, say, multiple things happening at once. So let's have a look at the earthquake that generated the Tohoku 2011 earthquake. So this is a block diagram, a three-dimensional representation of the crust in Japan. So we can see on the top, we've got the map, and then we've got the subduction zone going down underneath, where the Pacific Ocean is going down underneath underneath Japan. And all those blobs, the red and green circles, indicate the location of earthquakes underneath the ground along the subduction zone interface. So we have that top slab going down, and there's friction along that with the continental crust, and that causes a range of earthquakes. And subduction zone earthquakes are the biggest earthquakes that can form because the faults are very, very large in comparison to other tectonic structures that you find in other locations. And so we get this concentration of earthquakes along this interface called the Benioff zone. And the Tohoku earthquake was a rupture of this subduction zone interface. And it generated a magnitude 9 earthquake. Earthquakes release energy, but they also move rock. And so it's the movement of the two bits of rock against each other that releases energy. That's the earthquake. And of course, the motion then can displace anything above it. On land, it will displace the land. But of course, in the ocean, when the crust moves, it will displace the water column above it, and that generates the tsunami. So when we talk about the Tohoku earthquake, it's a magnitude 9, so that's about as big as an earthquake can get. The epicenter was around about 150 kilometers offshore, but the earthquake rupture, that's the area of rock that moved, was around about 330 kilometers long. That is enormous. And in the major part of the slip, there was a maximum of 28 meters of slip along that subduction zone. So that is a really big displacement that then obviously is going to move a lot of water column above it. The earthquake itself lasted 6 minutes. If you think about how long 6 minutes is of shaking, that is really very large and would have been absolutely terrifying. And of course, afterwards, there were hundreds of aftershocks, and some of those aftershocks would have been magnitude 7 and 8. And so it really was a very, very large earthquake event, which then generated a tsunami that spread across the whole of the Pacific Ocean. And on the left here, we can see a map showing in those little bars the elevation of the tsunami recorded at different locations, and then the contour lines across the Pacific are the travel time in hours. And so you can see that 20 hours after the event, a tsunami of around 3 meters was recorded along the South American coast. So of course we hear a lot about the impact in Japan, but these are regional hazards that can cause a lot of effects elsewhere as well. On the right, we've got another photo of the tsunami coming on land, and you can see again that this is not a breaking wave, it's a surge, and it just keeps on coming. At the bottom right, we've got the Fukushima nuclear power plant. Now, of course, Japan was aware that it's earthquake prone and that there could be large tsunamis associated with subduction zone earthquakes. The Fukushima nuclear power plant wall was 10 meters high. it still was overwhelmed by this tsunami and, of course, caused the resultant meltdown of the nuclear power plant. So the question is, were people not aware? Well, we can go back into the geological past and get evidence for the past events that have happened. How big, how large, how often were tsunamis? And we can look at this in two different ways. So we can look at fine-grained deposits, so things like sand and mud, and we can also look for coarse-grained deposits, big boulders. So they have characteristics that are really different from a non-tsunami generated sediment. Sandy, fine-grained tsunami sediments are going to rest upon an unconformity. So an unconformity is a gap in the stratigraphy. Something has been eroded and then something else on top. And of course, that erosion is to do with the energy of that wave. The deposits are normally graded or massive. So what does that mean? A massive sediment has no internal structure. Something that's normally graded goes from coarse to fine grained. So we have these typical grain sizes. The actual thickness of the sediment thins inland, so it's thicker towards the shore, thinner as you go inland, as the energy of that flow wanes. And alongside that, the grain size, the size of the particles transported, reduces in size as well, due to the fact that the energy is reducing as we go inland. And it will contain marine fossils, but being otherwise a terrestrial set of sediments. So we can think of soils building up in fields or in floodplains, and then suddenly you could get a marine layer and then back to soils, and that could be a good evidence of a tsunami. You can also move really large stuff, and there's been some really interesting photos of recent tsunamis like the Tohoku, but also the Boxing Day tsunami in Thailand that has moved bits of coral reef or has actually moved sea defences. But if we were looking into the past, of course, we don't have things that we can definitively say were in one place and then were moved later. And so if we're looking at larger boulders, we need to have evidence that they were sitting in the marine realm first. So having some sort of bivalves or boring structures, something that tells us they're in the marine. And we need to be clear that they're not kind of landslide deposits. They haven't been transported down a local slope. It's helpful if they're kind of quite different from the local geology, because that helps us confirm that they have been brought in by a wave, and they need to be large enough that we can confidently say that these are not the result of a large storm. So boulders are a little bit more difficult to sometimes definitively say that these are the result of a tsunami. But we can use these different deposits to help us work out those things like run-up and inundation. So there's been loads of work in Japan looking at these, looking for tsunami deposits. So as you could see in that video, a lot of the coast of Japan is actually quite low-lying, and there are lots of lagoons and places that scientists have gone to take sediment cores or dig pits to look for the evidence of tsunamis. And you can see here in this peat, in this core, that there's layers of peat and sand, and the peat is the terrestrial deposits and the sand are incoming tsunamis, and quite a lot of these have got diatoms in. And so the geologists in Japan have got a really good record of historic and prehistoric tsunamis, large enough that they don't have any comparable equivalents from the modern times. Some of them reached 3 to 4 kilometers or more inland. Many had wave heights of much more than 10 meters. And they were occurring, seemed to occur on around about a 500 to 1,000 year recurrence interval. So the geological evidence was there. If you note, this paper was published in 2003. So sometime before the Fukushima nuclear power incident with the 10-meter high walls, there was evidence that they could have been breached. because there wasn't any records in the modern times, and the Japanese records go back quite a long time, then that sort of suggests that perhaps we should have been worrying about this. So the geological evidence was there, but there wasn't the political willpower, and of course it costs a lot of money to build walls more than 10 meters in height, and it felt that it probably wasn't needed, but of course it was. So that's Japan. I think that's a really interesting case study where the geological evidence was there, but the political and engineering establishments didn't think the geological evidence was strong enough. We're going to now come to the UK, and we're going to look at a landslide event called Strega. Now, this is a bit different. There's quite a lot of funding going into understanding this event in order to make sure that infrastructure, especially around the Scottish coast, are properly protected in the event that something like this could happen again. But I want to say straight from the beginning, it's quite unlikely that we will see a Strega type event in our lifetimes or even in the next few thousands of years. So let's take a step back. Strega is a landslide, a generated tsunami event. It happened around about 8,200 years ago, where part of the submarine slope failed. So on the edges of the continental coasts, we have the shelf edge marked by the dashed line on the map on the right hand side, and you can see here that the Strega slide is an area that begins at that shelf to slope transition. It is the most recent of a whole series of submarine failures that have been recorded in the region, happening on around about 100,000 year interval. So we've got the Tampan slide around about 100,000 years ago, the R slide 300,000 years ago, the Moore slide 400,000 years ago, and the S slide 500,000 years ago. And that's really interesting. The shelf edge is quite steep, it's at around about 35 degrees, whereas the actual slope that the Strega slide is going down is much shallower, only at about 1/2 to 2 degrees. But you can see that when we get into the basin, there is topography in the basin that the Strega slide, the deposits from that are moving around. So let's just have a look at a little video that's put together to show the tsunami that would have happened. And so we can see in the red an increase in sea level, i.e. the crest of the wave, and then the blue, the trough of the wave. And so this is a model developed by scientists at the University of York to try and understand, based upon the physics of the event, where waves could have hit. And you can see really clearly that Iceland, Greenland, the coast of Norway, and the United Kingdom are very strongly impacted by an event of this kind. If we just run that again, we can see these dark reds have an amplitude of 5 meters, and they are hitting the Shetland Islands in the north of Scotland in particular at those sorts of elevations. So clearly, if you live in those areas, you might be concerned that this event could happen again in the future. And something we've been doing at the University of Plymouth is modelling this type of event. So this is just a bit of an aside, just to show you sort of a lab experiment that we run here in our marine laboratory. So this is a landslide coming down and causing a tsunami on the top. It's quite subtle because of the scale of the experiment. So I'll just play that again, and you can see the tsunami, the waves forming by that landslide coming down the slope. So just like in the case of the earthquake, it's the motion of the landslide that is moving, displacing the water column above it and generating that slide. So what caused the Strega slide? Well, it happened at the end or just at the transition between the last glacial phase and our current interglacial. So a range of different ideas have been put together to explain how this could happen. But it's not likely to happen again right now because we're not at that glacial interglacial transition, and at that time sea level was much lower than it is at the present day. So the position of sea level could have a strong impact in how some of these processes could have worked. So one idea is that there was perhaps could have been sediment loading. So that means that lots and lots of sediment was being shed from the continent into the ocean, forming very quickly thick piles of sediments that caused the underlying sediment to suddenly fail because of the extra weight on top of the underlying sediments. So that's one idea. That's because there were large glaciers coming off the Norwegian coast into the sea. Another idea that's been proposed is that, in fact, it could have been earthquake shaking that caused the failure of this landslide. So some of you might be thinking, well, Norway doesn't have a lot of earthquakes, but interestingly, if you weight down the crust with lots of ice in the glaciers, when you start to remove that ice, glacial unloading, you're changing the stress in the Earth's crust, and that stress change can actually cause post-glacial earthquakes, and some quite large ones, up to magnitude 6s, have been recorded in Norway. So it could have been that an earthquake shaking actually caused the failure of the Storegga landslide. Another idea that's been put forward is this idea of gas hydrates. So in the deep ocean, pressure is different. You've obviously got the water column, and it's quite cold. And as a result, you can form these ices of methane clathrate, but they're very, very unstable. And a bit of extra warming, which you would have seen at the end of the glacial period, or changes in sea level can cause these to sublimate, i.e. go from a solid to a gas. And of course, that is going to destabilize and cause problems in your sediment, and again could cause failure. As an aside, the climate scientists are really worried about these things being a contribution to climate change as we warm the oceans. So the current consensus is actually it probably was a little bit of a combination of a post-glacial earthquake and increased sediment supply causing sediment loading and changes in the sediment column that actually caused the failure of the Storegga slide. And we can see the effect of that by mapping and going to the adjacent coastlines. So there's been lots of work to try and see if that model that the computer physicists have put together actually bears any resemblance to real life. Lots of people can make models of physical processes in a computer, but it's really important that we can get field information to confirm if those models are realistic or whether they're completely wrong. So along the coast of Norway, and the Shetland Islands, Faroes, a little bit of Iceland and Scotland, a lot of geologists have been going to see if they can find evidence of this proposed tsunami. And this map here shows the elevations that they've been mapped. And you can see in Shetland, sediments have been mapped that have been related to the tsunami at more than 20 meters above present day sea level. So that is quite significant if we remember that sea level was lower when this event happened. And these have been confirmed because of some of those things that I mentioned earlier. So there's presence of marine fossils in those sediments, there's landward fining, i.e. the grain size of the sediments gets smaller as we go inland, there's evidence of erosion towards the coast. There are things called rip-up clasts, and they're basically just bits of sediment that have been ripped up by turbulent, energetic waves, and lots of erosion, massive and normal grading that I mentioned earlier. And these elevations far exceed some of the estimates based upon those models. They've been dated, so carbon-14 dating has dated these deposits to be within error of the slide. And interestingly, the wave heights are closer towards where the slide happened than further away, which is again what we would expect. So there's really good geological evidence of this slide. And here's just a few pictures. showing we've got peat. So in Scotland, obviously, we've got lots of peat generation, and then we've got this tsunami deposit in the top right, sandy with these blocks of peat, and these are rip-up clasts of the underlying peat that have been torn up by the energy of the wave. How do we figure out the run-up height? How do we know what the elevation was at that time? So one way they've been able to do it in Scotland and Norway is that there are a series of little ponds and basins at different elevations. And so if the tsunami reaches a lake or a pond at one elevation and fills in material there, we can say that it got up to that elevation but didn't get up to the next one. So we actually just go and map and work out the elevations. That's fairly easy with events in the recent past. So that's the Storegga. There's lots of research going into this event, but the likelihood of it happening at the present time is low, because we're not in that glacial interglacial transition, which is when the events tend to happen. However, where do tsunamis occur in Europe? Where might we be affected by this? And one place is the Mediterranean. So I'm sure many of you have gone on holiday to places like Italy or Greece, even Spain or Turkey, in the Mediterranean region. And these are places that could be affected by quite large tsunamis. And this is because of the active tectonics in the Mediterranean. So the Mediterranean is a collisional zone. Africa is moving northwards into Europe, and there are a whole series of different structures accommodating, taking up those great strains. And this red band is more or less the plate boundary between the two areas. You get lots of earthquakes in this area, and if you get lots of earthquakes, then there is the potential to generate tsunamis if those earthquakes are taking place under the water, or potentially generating things like landslides that could then also form tsunamis. And we know that this is a possibility because of an event that I've worked on. So I've worked on something called the AD 365 Cretan earthquake. And this is a really stunning event, and we haven't seen anything like it in recent times. So in AD 365, towards the end of the Roman Empire, there was a really large earthquake in just off the southwestern coast of Crete. And the estimates are that it was probably about a magnitude 8.3. So this is really big. It caused uplift of up to 9 meters of the coast of Crete. So if we look at the photograph in the top right, you can see there's a line on the cliff there. That's the previous sea level, which had been eroded and then had been uplifted, brought out of the sea by this large earthquake. And there are these fantastic quotes from the historical records. For the mass of the waters returning when least expected, killed many thousands by drowning. And with the tides whipped up to a height as they rushed back, some ships, after the anger of the watery element had grown old, were seen to have sunk, and the bodies of people killed in shipwrecks lay there, faces up or down. And so it really brings home to you the impact that this event had on the Mediterranean peoples at that time. And it really was quite devastating. So it happened off the coast of Crete. It had significant effects on the local populations, but it was also recorded as far along the coastlines of Greece. It caused significant damage in Alexandria in northern Egypt today. And in Cyrenaica, which is now in present-day Libya, it completely destroyed the city of Apollonia. And so Apollonia was a port town, quite significant at that period, and it basically wiped out all the infrastructure. And so this is Cyrenaica today. These are these bits here, the remnants of basically a large harbour structure. And so there is good historical evidence that large tsunamis occurred in the Mediterranean region. And so some of the work that I've done is actually go to Crete and try and find evidence of this event to see if we can get more scientific information rather than hyperbole from the ancient observers. So I've been looking at boulder deposits. So these are some boulder deposits that we identified on the southern coast of Crete. They have evidence of marine origin and movement. They have that bathtub-like erosion ring in some of them that shows they were at sea level and have since been moved. They have a range of compositions that don't correspond to the local bedrock geology. And so we can be confident that they haven't moved down slope, but they've been moved inland by a wave. And their size, if we do a bit of maths, we can work out that their size would mean that storm waves would be highly unlikely because they just don't get that big in the Mediterranean basin. That's been corroborated by other workers who've seen evidence of fine-grained tsunami deposits, like the photograph on the right. These are from the west coast in a Roman port that was damaged and became obsolete as a result of the uplift and the resultant wave. And we can see here a line of shells that were brought in by the tsunami wave. So these are marine shells and now in terrestrial sediments. And again, we see things like landwood fining and erosive bases. And I've dated and others have dated these deposits, and they correlate well with this AD 365 event. And they show that there would have been several meters of inundation, and they corroborate the historical records very well. So what caused this tsunami? Well, again, it was probably a subduction zone earthquake. There was some debate about whether it occurred on the actual subduction zone interface or not, or whether it was a large fault within the overlying crust. I think that's perhaps less important than the fact that it caused 9 meters in uplift in the tsunami, though. But there has been some modelling, again, using these parameters, using the geological data to try and visualise the impact of the tsunami and how this event would propagate through the Mediterranean. And you can see here that we have 2 meters of sea surface displacement, and that correlates well with the geological evidence that has been found. Now that might seem lower than the 10 meters, but if you bear in mind that actually a lot of Mediterranean coastlines are very low lying, there's often not a lot of topography, then of course this could be very devastating if it were to occur now with the build-up of hotels and tourist resorts often right at sea level. So hopefully, if you've been to the Mediterranean or going to the Mediterranean, you will see that there are tsunami evacuation signs in critical places. And some places I've been have this and others don't. But I think if you are going to somewhere that has earthquakes, then these are really good messages to take home. So this is actually from New Zealand. New Zealand have got really good earthquake and tsunami education, and they have these little sayings. If an earthquake is long or strong, get gone. So that means if an earthquake lasts for more than a minute, if it's so strong you can't stay on your feet, then go to the nearest highest ground, because they're the earthquakes that are likely to generate a tsunami. Without waiting for any warnings or anything, just go. And if an earthquake happens in general, just drop, cover and hold on. Don't run outside, don't go stand in the doorway, get to your knees, find cover like a table and hold on. And so they're really good things to keep in mind if you're ever going anywhere with earthquake or tsunami risk. So I'd just like to finish by just saying a few things about our geology programs at Plymouth in case any of you are interested. We offer a range of programs here at Plymouth. We have a foundation year program, then we have 4 BSc, Bachelor of Science programs, and a Master of Geology program. So we offer straight geology, physical geography and geology, geology with ocean science, and environmental geoscience. And they all have slightly different flavours and different focuses. So if you're interested more, then we can answer your questions and give you more information at the end. And I'd just like to point out my fabulous colleagues. We are a really strong geology group here within the School of Geography, Earth and Environmental Sciences. We're field geologists. We've got a huge range of expertise across our staff. We're all active researchers. That's really important at university. And many of us are interested in hazards of various types: tsunamis, earthquakes, volcanoes, I've already mentioned tsunamis, landslides. So that's me finished. I really hope that you found that interesting. I can see that some questions, so I'll just stop sharing my screen. And I invite Shauna perhaps to reveal herself. Shauna works in faculty and is going to just help me field questions.
Hi, Sarah. So we've got quite a few actually, which is good. So going back to the Storegga event, we've got a question about Scotland and how it's risen isostatically since the Storegga event. Could this partly explain the altitude of the Shetland Islands?
Yeah, so that's a really good question. Yes, you're right. After ice melts, the land rises because the ice is so heavy that it actually depresses the elevation of the ground. And since the melting of the ice caps, the ground has risen up, but it hasn't risen up that much. There are really good controls on the amount it has risen, so we can use things like marine terraces to actually document the elevation change. And so that's taken into account when the scientists go and look for data. We can work out how much the glacial rebound has been. We can work out what elevation the sea was at that time compared to now, using models of sea level change. And so you can take the modern elevation of something and then you can work out what that equivalent would be today and what elevation it was when it formed. So yeah, there's still a big difference though. These are still big waves, even though there is that post-glacial rebound to take into account. Yeah.
Amazing, thanks, Sarah. Can we use run-up to estimate a tsunami's wave height, and if so, how?
Okay, so there are a range of mathematical equations, basically. So it's not only geologists who are interested in tsunamis, there are physical modelers, oceanographers, all sorts of people work on these problems. And there's been quite a lot of work done in wave tanks and in flume tanks, modeling different parameters of tsunamis, and looking at the relationship between things like run-up, inundation, and the physical parameters of the waves. So if you can go and make measurements of some of these things, you can then plug them into equations and calculate things like amplitude and wave height and stuff like that.
Cool. What impact do videos and live feeds of the Japan and Boxing Day events do to help the study of tsunamis?
That's a difficult question. That's an interesting question. How do they help the study? Well, I guess this could be answered in a couple of different ways. One is that when we're looking at past events, we've only got kind of fragmentary bits of information. So it's sometimes difficult to really understand how these physical processes work. So when you've got video recordings and actual real-time measurements, you've got better data that you can then apply to past events. So that real idea of the present is the key to the past. The other thing is that it's just visualization and making people aware. It's really, really difficult sometimes talking about events that happened in the distant past, because people don't necessarily understand why that's important to them or how it applies to them. And so by really seeing that in action, it can make a big impact and really change the way that the general public understand the importance of knowing about these events and understand that these are really dangerous. And unfortunately, a lot of people do die every year, and it's heartbreaking for those families. But hopefully, the work that we do can make places safer, because we can understand the science, and then we can communicate that to the people who live there, who then will hopefully have a better understanding of these events and take the right actions to make their places of work and home safer, and know what to do in the event of a big tsunami or earthquake or other natural hazards.
Thanks, Sarah. Do tsunamis play any role in eustatic or isostatic change?
No, they don't. They are short-lived events. Global sea level is controlled by temperature and ice cover primarily, but also to a certain extent by the activity at mid-ocean ridges. So there's a range of factors that go into setting what sea level is globally. So that's eustatic sea level. What tsunamis can do is change local sea level through flooding of low-lying areas, and shaping the coastlines, and that can often happen at the same time that there's local changes in land level as a result of an earthquake. So earthquakes can cause the land to go up, known as uplift, or they can cause the land to go down, known as subsidence. And so you can have local changes in sea level as a result of these events, but it won't affect global sea level.
Okay, thank you, Sarah. How did scientists first find evidence of events such as Storegga?
Well, I don't know the exact story of how Storegga was found, but a lot of it's serendipity. It's just luck. So it's going out into the field, it's looking at something and then going, hey, that's a bit weird. How did that get there? How did we get marine fossils in a coastal record? And so it's by going into the field, making observations, and then finding things that you're not quite sure of and questioning and interpreting those data. That's how we find out about these things. Yeah.
Just happening upon them. Okay, we've got two more unless anybody's got any others. So does the shape of land or cliffs give us any information about where tsunamis have occurred before and how large they have been?
In some cases it can do, but more often the pre-existing shape of the land will influence where a tsunami will go. And so we see this all the time with recent events. If you think about a cliff meters high, then that's going to be very resistant to any type of waves and won't record any sediment or any impact of a large event. But as soon as a wave can overtop something, is higher than a cliff or higher than the local land, then there is the potential for erosion by the wave, and there's the potential of deposition of subsequent sediment. So if we're interested in finding evidence for tsunamis, we can use the shape of the land to help direct us to places where we're more likely to find material. So especially if you want to find fine-grained tsunami sediments, then the best place is to go somewhere low, perhaps with a lagoon or evidence that there was low-lying topography in the past, and they're the places you're most likely to find traces of tsunamis.
Cool,
I hope that answers your question.
Final question. Is there any way of extrapolating the uplift data to calculate tsunami's height, or are there too many other variables involved?
Well, there's sort of two different things. So the uplift height is more telling you about if we're talking about an earthquake tsunami, it's more telling you about the earthquake that happened and not necessarily the resultant tsunami, because uplift isn't quite the same as displacement, and so it's very tricky to decouple and know the relationship between those different things. But you could probably make guesses, because there are good relationships between the length of a fault and the amount that it would move, and so you could make an estimate based on the amount of uplift on what the displacement on that fault was, and then you could probably do some back of the envelope calculations to think about how big the tsunami was, but you would really want some other information.
Okay, thank you, Sarah. We've had one more sneaking in with another question. Do you think we will ever see the North Sea dams constructed?
Okay, so yes, I've heard this idea before. Probably not. I wouldn't have thought so. One, I think they've been. This is not something I know a lot about, so I really hope I don't get this wrong. But I thought that idea was about sea level change rather than tsunamis, to protect like low-lying countries like the Netherlands and stuff, where they're very at risk of sea level rise from sea level. That's what I understand those to be, but I stress that it's not something I know a lot about. And I think the scale and the cost of doing that, and the fact that it would need to be a multinational effort, and we don't know what the effect would be on the ecosystems in the North Sea, I find it very difficult to believe that would be a good way of spending money when there would probably be better things we could spend the money on, and it certainly wouldn't help us prevent something like Storego, I don't think, because it's not really a risk to us at the present time under present day sea level scenarios.
Thanks, Sarah.
As far as again, caveat all of this, as far as I understand. Yeah.
Do a quick Google afterwards. Oh, we've got another one. Oh no, that was just a thank you. Thanks for your time, Sarah, and thanks to everybody else for coming. I don't know if you had anything else that you wanted to add before we wrap up, Sarah?
No, just thank you all for listening today. I hope you've enjoyed it. And yeah, thank you very much.
Thanks for coming, guys. There will be a recording that we'll download afterwards and send out so you can watch again at home or share with your other course mates. But yeah, have a lovely day and we'll see you soon.
Thank you.
Bye.